This paper is gonna deal with specific attention problem in large language models and make the training of large language models faster and require less memory. So you know that the attention mechanism is scaling quadratically. Computations are scaling quadratically with the sequence length. So if you have one long document, long sequence, it will require a lot more computation than if you have same number of tokens but divided into multiple smaller documents. So then all those smaller documents, their quadratic scaling is not as big as one long document quadratic scaling, even though the amount of tokens is same. So then if one GPU gets the long document and the other GPU gets the short documents, then these short documents one will compute a lot faster and it will have to wait for this big to compute. So that's inefficiency. So that would happen if we are dividing by the number of tokens in data parallel ways. So for example, this can be done if each GPU has its own instance of model, and then we give like 4,000 tokens here, 4,000 tokens here, they process and then combine gradients and learn and update every model. But as I said, 1 times 4,000 and 4 times 1,000 token documents is a lot different. So this one will finish a lot faster. Previous methods try to solve this in different ways. For example, you could just give more tokens to the one that has less attention, but then you need to use more memory here, so now imbalance is in memory, even though computation is balanced. Another method would split this long sequence across multiple GPUs, but then you need to calculate keys and queries, and you need to all reduce or combine them, so you have extra computation or communication overhead if you're splitting it like that. The solution is very clever. So the problematic part is the softmax attention. So softmax of query matrix times key transposed, and that softmax times value matrix. That's the problematic part. Now, this doesn't have any weights to learn. So this is not learning anything. So we don't need to worry about weights, backpropagation gradients here. So this can be pushed to any available device without needing to keep track of anything. Just compute and then return, and that's it, we're done. So the balancing becomes simple task scheduling problem. And interestingly enough, you can combine independent attention calculations from this part of the text, from this part, and do all of that together in a single kernel. So it's similar to flash attention, just grouping up a bunch of as much stuff as possible, doing it all at once. So we don't need to communicate, send around data within the GPU and load kernels and stuff. So those are the two insights of the authors. The solution authors propose are attention servers. So attention server is a GPU that's gonna calculate, that's gonna get this data to calculate this attention. Now, it doesn't need to be only for attention. It can actually have its own parts of the model. It can be GPU that's already doing like feed forward and other parts of the model. But it can also act as attention server after or before and after it's doing this other stuff. Let's say we have 512 GPUs and all of them have their own model doing their own stuff until they come to attention mechanism part. So then they will all wait for everybody to get to the attention mechanism part. And then you have central scheduler that will take all of those attention that every GPU needs to calculate and split it amongst those same GPUs, split it such that every GPU has roughly the same or same amount of flops, same amount of compute to do. So it's gonna mix up all of the attention necessary to distribute them throughout GPUs. Once attention is done, then every GPU gets back its attention scores, whatever it needs, and continues independently. So here the logic is they will always, almost all finish at the almost same time. So at every part, it won't happen that one GPU has huge attention, so every other GPU needs to wait. That's included in that data parallelism or pipeline parallelism with that GPU. It's important to understand when this attention part happens, this central brain scheduler will collect, or it will be aware of all of the attention that needs to be done, and it may split. For example, if we have huge attention computation, it will split into smaller parts and then split it across GPUs. And it can happen that one GPU gets tasks from multiple different GPUs, and it will combine all of those tasks into a single kernel, single computation, and do all of them at once. This is a good example here. You have one document that has 4,000 tokens. You see this triangle, but here you have 4 documents that have 1,000 tokens. It's actually a lot smaller amount of this blue, a lot smaller amount of computation. So all of this is not necessary computation compared to this. And so a lot of idle time for this guy, waiting for this guy to finish if they are, for example, in data parallel. And Gemini gave a good example here. So when we are splitting this big softmax attention into tasks, it needs to be split so that GPU that gets that task has all of the information to perform that task. For example, a task can be to just calculate a query times all of the previous keys. In that case, it needs to have that query and all of the previous keys. And also, one GPU can be tasked to calculate attention of the first half of the sequence, of the first half of the tokens. And so it just needs keys and queries and values of the first half. But then this other GPU that calculates scores for the second half needs actually those queries, but all of the keys and values, including the first half. So the system must give it all of the keys and values, but just queries for the second half because it only needs those. Now you would see that there is a bit communication overhead because so many different tasks sent to so many different things divided, but we can actually be transferring data while calculating as well. So at the same time, so there is no waiting for data to come and then calculate. So we can parallelize different tasks like this. The paper talks about that as well. That's gonna be it for this video. Join my school to become AI researcher. We have all of the courses for free for some time. So get a lifetime access for free before I make it paid. Link below the video.